presentation for today will focus on what we call planetary causal inference. So you're in a class on, geospatial analysis with connections to urban planning. And today we're going to talk more about the satellite imagery side of things. And we're going to have two different aspects to the discussion. And we're going to try to unify them at the end. So the title is Seen Like a Satellite While Learning Across Scales, Remote Audits of Randomization in Multi-Scale Representations for Heterogeneous Effects. So we're going to use the same data source in two very different ways in order to help support our analysis of either experiments or observational data. So whether you go on to a career that deals with experiments or whether you go on to a career that deals with observational data, some of the insights that we talk about here will be relevant to that. So I'm excited to get your feedback, have this discussion, and discuss some of the material with you today. That's the big picture overview. And I should just pause, are there any questions before we get started or any things that are coming up before we're getting started? Let's get started. Just to presage some of the findings, we're going to use Earth observation data in two very different ways in this talk. In the first way, we're going to use satellite data to probe the integrity of experiments or to probe the integrity of research designs. This is also related to some of the ongoing work that Kaz and I are involved in, but we're going to talk about something called the remote audit, and we're going to use imagery to confirm some of the assumptions about how an experiment was designed. And this is going to be relevant for flagging potential issues and also for auditing the potential trustworthiness of data vendors or other potential issues in the data generating process. And here, Earth observation data are going to be like almost like a neutral arbiter of truth. I, as an individual, or most governments as governments, don't have the ability to mess with the remote sensing data. They can't go up to the satellite and change what's being collected by the satellite. So there's a certain neutrality. There's a certain kind of powerful separation between any private individual and these satellite data that are going to be really useful. That firewall is going to be really useful as we use imagery to actually audit our analyses. So that's case number one. But case number two is more about scientific usefulness. How can we use imagery in order to make sense of what's happening within an experiment or within an observational study? And we're going to talk about something called heterogeneity, treatment effect heterogeneity. I'm going to walk you through what that means later on. So if I use too much jargon or if I'm talking about things that you don't have context for, just interrupt and we can talk about it. Since there's no bad question, really, it's up to me to try to convey the material clearly. So if you have that question, I'm sure someone else does too. So these are the two complementary problems that we're going to try to talk about today and resolve in kind of use Earth observation in pursuit of better answers. So the payoff of this unification is that both before measurement and also during and after analysis, we're going to be able to use satellite imagery in order to improve our understanding of what's happening on the ground. That's the big picture. I know it's a lot of words on this slide, but the next slide is just images. So this is a running picture of what I want you to have in your head during this presentation. It's a picture on the left of the Washington Longfellow House here in Cambridge, Massachusetts. So this George Washington, I think in 1776, actually lived in this house. So you have this house, and this is a satellite image from that house. This is, I believe, a Maxar image. And you can see, first of all, the incredible detail. We can see all the different walking paths around this house. We can see the degree to which there is foliage. From this image, we can tell the season. Ask yourself, is this spring or is this winter or is this summer or is this fall? And pretty clearly, this is summer. The trees are they have full foliage. We can even tell that they've been watering the grass. The grass seems green. There's no patches of gray or brown or black. So this is an image of that household, but that same household is also in the center of the right-hand image. So we have the left-hand image, we have the right-hand image. And both of those, in a certain sense, are a picture of the same place from the satellite. But the information contained within the two might be different. So you could ask yourself, what information, I could maybe even just pose this to the audience. What information does the image on the left contain versus the image on the right? So we can just pause to reflect on this and feel free to interject in answering that as well. Eric, what are your thoughts? What does the image on the right contain versus the image on the left in terms of information capacity? Putting Eric on the spot. I think that I see when I look at the image on the right is I see the broader neighborhood. I see that this household, It's in a suburban area. I don't see major thoroughfares coming close to it. It seems to be in a relatively suburban environment. There is an more urbanized district to the north. Then to the south, there is this river. So this information, for some purposes, it might be very relevant, but for others, it might not be relevant. And one of the things that we'll talk about in the second part of the presentation is how to more rigorously quantify that information gap between the more local scale and the more global scale. So you can think of satellite imagery almost as a infinitely complex hierarchical data stream. You can zoom in and you can zoom out. And we're going to ask ourselves how to do that in a principled way in the second part of the talk. But this is just giving you a visual of what satellite imagery are. These are basically pictures taken from space, and these are high resolution imagery, but the resolution might vary based on sensor. So there are in space multiple sensors from multiple governmental agencies, from multiple private providers that are all trying to do the same thing. And that thing is to collect a universal corpus of what's happening on the ground across the entire world on a daily or weekly basis. I think that's giving you some hint, I hope, of the potential power of imagery. So having motivated that, let's talk about how we can use this in our downstream analysis. So yes, it's a cool data source, but what can I do with it in my analysis? Is it just a pretty picture, or can I actually use this pretty picture for some deeper scientific or policy inquiry? And the first way in which we'll discuss this is in the design of experiments. So some of you may go on to work for NGOs or for governments or for research organizations that run RCTs. And what we're going to talk about first is how we can use those pre-pictures that we just looked at to audit experiments, to audit RCTs, to audit other forms of research design in an interpretable way. So we're going to use those images to try to audit experiments. And what do I mean by that? Well, let's start with an example. And this is the example that we're drawing from here. It's this research note about a curious paper, Islam 2019, that was published. And what this research note found is that there are actually some anomalous aspects of the experiment. So this research note flagged some issues about this other paper, this Islam 2019 paper. And this note observed that although randomization of this treatment to schools was purportedly random, when they broke it down by administrative area, they observed that all of the schools within these administrative units were treated, and all of the areas over here in these administrative units, in these 4 administrative units, were in the control group. So, randomness, this seems highly not random. By randomness, you would expect that maybe 52% treated, 51% of the schools are control, maybe 55, maybe if it's a bad randomization, maybe it's like 70%. But we see that there is administrative unit after administrative unit, things don't appear to be as randomized as we thought they were. And there are also deeper anomalies in terms of how this study completely overlaps with the previous study that was in fact retracted due to a similar issue. So there are these potential issues in this experiment, and not only are there issues with randomization, but there are also potential issues with selection. Is the place that was included in the sample similar to other places that were outside of the experiment, or are they different to it? Like ultimately, if I'm a policymaker working for the World Bank or working for the IMF, I want to do an RCT in a way that allows me to make broader inferences, not only about this part of Uganda, but about all parts of Uganda, or this part of Bangladesh is the case is here, or all parts of Bangladesh. So there's a sense in which selection dynamics are critically important to making generalizable insights. Is there a way we can use those pretty pictures we just were looking at to try to, on a very low cost and very fast basis, flag some of the potential issues about lack of representativeness, or even potential fraud within experimental designs, as the case may be, or potential serious implementation flaws? I pause just if there are questions, if there are comments, feel free to interject as we get the next slide ready. So a remote audit is essentially using satellite imagery to try to figure out whether there are systematic differences between areas that were in treatment versus areas that were in control. So let's just go back to this example. We have all of these areas over here in yellow, and then all of these areas here in blue. What we're going to do is we're going to take pictures, we're going to take satellite imagery from these areas that are yellow, and we're going to compare them against satellite imagery of these areas that are blue. And we're going to ask ourselves, do the pictures look similar or do they look different? I can do that, before the experiment ever starts. I don't need to send my $2 million, per day team to this part of Bangladesh to actually get that information. I can get it from Landsat, which is one satellite provider, or I can get it from Maxar, which is another. I can get that information at any time before, or I even get the grant to run the experiment. I can do this sort of analysis. So what we're going to do is we're going to compare places that were treated, and we're going to compare that against places that were assigned control. And we're going to basically ask ourselves, does the imagery predict that random assignment? Let's ask yourself the following question. Should the imagery predict assignment or should it not predict assignment? Let's just dwell on that for a minute. Clearly, if this is an RCT, if this is a randomized controlled trial, the imagery shouldn't predict assignment. The imagery should be independent from the treatment. In other words, if the experimental allocation, in other words, if the coin flip about whether this school got the treatment or didn't get the treatment, if that coin flip is truly just a coin flip, then the imagery is not going to predict it because there's no signal in the imagery about the treatment assignment. And what we're going to do here is we're going to basically check for the presence of that pathway. If there is such a path between the image and the assignment, that's a flag. That's a red flag. That's an indication that there may be potential issues in the experiment. Maybe it's an issue about, my contractor didn't actually do a random assignment. Maybe my contractor just went to, schools over here. And because it was convenient to implement the experiment in this northern region, they gave the treatment there, but they didn't get the treatment down there because it wasn't convenient. So maybe there's an issue with my contractor. Maybe there's some other deeper issue that I need to address. So what the audit is going to do is it's going to ask ourselves, is the imagery, which here is just denoted by the letter N, is that imagery associated with this treatment assignment, which you could call A, or is it not associated? Is it associated or is it not? If it's associated, then ask yourself the question, does the audit fail or does it pass? If there is an association, the audit, in a sense, fails, or at least it can't be said to succeed. In the sense that there is this signal between the imagery and the treatment assignment. This imagery, from a deeper perspective, your policymaker friends at the World Bank or at the IMF, they might ask what exactly the image captures. We got satellite images from all the treated villages and compare them to the control village. What exactly does that capture? We're going to sidestep the issue for the moment. We have some answers towards that, but broadly speaking, the imagery, we think of it as capturing a bundle of interconnected factors related to local context, local latent context. So this could associate with things like, type of agriculture. Certain types of agriculture leave a certain signature and so forth and so on. So we're not going to, in a sense, go too deep into that black box now, but maybe for your, for research, for your final projects or for downstream research, you or even we could think more about what exactly that latent context covers. But that's the intuition behind a remote audit. We're going to try to predict the imagery, predict the treatment assignment using imagery. And if we can do it, that's in a certain sense bad. If we cannot do it, that's in a sense good, because that means the treatment assignment actually was random as it was stated to be random. And I should just briefly note that this same exact audit process is also can be extended to address selection and missingness dynamics too. So that's just me saying you can do the same thing we just did, but change the question to not ask about treatment versus control, but instead to ask about, for example, are you in the sample or are you not in the sample? In other words, if there's a strong difference between areas in the sample versus not in the sample in image space, that's an indication that the places that got the treatment, but the places that were in the study and not in the study were potentially very different. And that could motivate follow-up work or could motivate other methodological tools to address the potential difference between one and the other. But this is the remote audit as we've conceived it.
One thing is that the context is going to make a big difference, right? Because if you have a large enough area, they might start to all look similar. So then it becomes very difficult to assign or predict assignment, which is maybe a good thing, but maybe in terms of specificity of the remote audit, it's not a good thing, right? So how do you make sure what scale that local context should be?
Good question. So this is going to connect, if we have time, to this multi-scale concatenation question that we'll talk about later on. But just to reiterate the question for the group, let's imagine we have, well, let's actually go to one of our studies down here. So each one of these points is a household in this experiment. You can notice how some of these households are really clustered together, but then others are really not clustered together. Imagery we have imagery for this entire place, for all of Uganda. This is Uganda. We have imagery for all of these places. So one question is, how big should our imagery be around each of these places? How much should we zoom in by, or how much should we zoom out by? There are two answers that I would give to address that question, Kaz. One answer would be use the multi-scale concatenation approach that we'll talk about in a few minutes, which is just take bigger images, like from a bigger region, and combine them with smaller images from the local context. That way, you'll get the best of both worlds. If there is overlap, you'll still be able to extract the broader signals of more contextual factors, while also preserving information about the specific household. So multi-scale concatenation will be one approach. Another approach would basically be to run the audit multiple times for different scales. Basically, scale is like a hyperparameter. First, the scale is 16 pixels, then it's 32 pixels, then it's 64 pixels, and so on and so on. And you can actually run the audit multiple times and take the maximum t-statistic from each of those analyses. The maximum t-statistic from each of those sub-analyses becomes your t-statistic for sort of the overall analysis. And you can actually do the randomization test that we're going to talk about in a minute in a fully valid way, even if you have a lot of sort of scales in question. Even if you have a lot of submodels or scales, you could still actually perform a unified test using what's called a max t-statistic. So you basically take the maximum test statistic across scales within the randomization test that I'll talk about in a minute. Does that make sense?
Yeah, and just playing, I guess, devil's advocate, what if spatially it looks like these counties or something did not get treatment, but what if the remote audit finds that, yeah, within the selection that you chose, like the counties, they are random enough? How would that get resolved, I guess?
A good question. So I think, you're getting at an important question. We're doing this audit. We're using information collected from a satellite. Not everything is going to be captured within that image. Like, let's go back to this. In that household on the left, is it a happy family that lives there, or is there an unhappy family? What kind of institutions operate within that family? We really don't know. It's not. We might be able to pick up signals that are correlated with those things. Like maybe unhappy families tend to not mow the lawn, or maybe they do tend to mow the lawn, and that is picked up on in the imagery. But certain things like, whether the family uses blue eggs or brown eggs for breakfast surely is not going to leave a signature there. So in that sense, the remote audit is not a panacea. Passing in the remote audit doesn't prove randomization, or it doesn't prove lack of issues. All it can merely do is potentially find issues that are correlated in some way with the visible environment present within the local context. Does that address your question?
No, yeah, I think it's good because I think, because we already have these geographic boundaries, which are not random, but then I think the satellite images helps to add some more information that maybe you don't get to see if you just say like, okay, here are like county boundaries or geographies, then maybe there is still some kind of randomness being selected within it. But yeah, I think there's a little bit of difference between, okay, like what is like classical, like administrative boundaries, and then maybe what we see as from like a satellite image remote sensing view as well.
Definitely. Here there could be a strong, like maybe on the north side or the south side of this road, maybe one side is Cambridge and the other side is Boston or Alston. We wouldn't necessarily be able to see all of that here. So you're totally right. I think one benefit of using imagery is that it is universally available in a unified way. If there's this famous study, this multi treatment graduation study, and it was conducted in Peru and Honduras and a few other countries, like 3 or 4 countries. So think of the administrative differences from country to country. Each country has their own way of doing censuses. Some countries might have good like precinct level data, some might not have it. So I think beyond kind of universal availability, there's also just the way in which the data is available in a unified way, which can help sort of speed up these sorts of audits. So that'll be another way to address that point. But you're right, not all factors or administrative quantities will be contained within the imagery alone. Great question. Going back to our discussion here, we have this latent context, we have this visualization of what we're doing. And it's important to discuss what we can catch here or what we cannot catch here, in line with the discussion that Kaz and I were just having. Certain image image aligned deviations will be detectable, but certainly not everything will be detectable within this sort of remote audit paradigm. So that's just important to note, and it's enduring limitation of this sort of framework. Here's some technical details. I'm probably not going to do too much going through the details here. The intuition, though, is that we're going to basically try to predict the treatment assignment from the imagery, and then we're going to get a summary of that prediction quality, and then we're going to subtract off the prediction quality we get if we just predict the baseline like treatment rate. So this value should be 0 if our predictions from the image are the same as the true treatment probabilities. If we do have a big signal, so ask yourself, if there's a really big signal in the treatment image linkage, this test statistic is, if you think about it, it's actually going to be positive on average, because this quality measure, this log likelihood, is going to be bigger than the log likelihood we would get if we just predict the baseline treatment rate. So in the paper, we talk about why we chose this test statistic, why we think it's useful. Really, any test statistic to some extent would do, but this one is nice because it's naturally ordered on 0 and it's one-sided. So if this test statistic is really big in a positive direction, that indicates that there's signal. If it's 0, that indicates that there's not signal. And we can generate p-values using a conditional randomization test. So that basically just means what we're going to do is we're going to take this same exact approach of calculating a test statistic and recomputing these predictions. We're going to do that exact same thing, but we're going to resample the treatment assignment vectors. In other words, on my computer, I'm going to generate synthetic experiments. Like, what if I regenerated the treatment assignments again and again and again, and then tried to predict those treatment assignments using the imagery again and again and again? I'm going to get a test statistic for every one of those synthetic experiments. And I'm going to compare the treatment assignment that I'm going to compare the test statistic that I observed in the real experimental draw from the set that I'm getting from this resampling process. So this is how we're going to calculate significance. Since we're using potentially very complicated machine learning models and things are getting complicated. So one way to simplify that complication is to use this sort of randomization test. If you're not big into stats, don't worry. The basic intuition is just that we're running a lot of synthetic experiments where we know the treatment shouldn't be associated with the imagery, and we're comparing what we observe against that baseline. And that's how we're assessing uncertainty here to get finite sample valid p-values. And there's some references here for those who are into the stats who want to dig into a bit more of the details. But I have here listed out an auditable workflow. So you might know that you might hear the term pre-registration. If you're running an experiment, one thing that you'll often do to increase the sort of legitimacy of your study is you'll write a little report about what you're going to do, and you'll send that to a centralized authority. And that pre-registration report, in some cases, actually is published as an independent publication. But that pre-registration is important to address issues regarding p-hacking. Basically, it gives the broader research community your early plan so that we can compare what your final study ends up being against that earlier plan to see, did you do what you said you were going to do, or did you sort of make a lot of ad hoc choices in the meantime that seem a little bit suspect? So what we're going to do is we could take this audit and pre-register the audit. And here are my sort of suggestions for what that pre-registration would look like. But the big picture point is what you should do is specify your design. Are you doing just a randomized controlled trial with or without blocking? Tell us what imagery you're going to be using. State how you're getting predictions from the imagery, which is something we could talk about as well. And then state how you're going to perform this resampling process, and then report p-values, reference histograms, seeds, and so forth and so on. So this is really just more for reference than anything. Like I said, the slides are already online for those who are curious. And you can use this in your next pre-registration report if you want to basically get a good sense for how your experimental design is actually shaping up in practice. I should also note, if you I have a little thing later on. If we have this decision tree about what you can do, if this audit flags different things, like what if you are starting to plan your experiment, but all of a sudden you run your audit and you find that, oh, maybe the imagery are actually predicting treatment assignment. What do? There are here, things you can do in the randomization case, in the selection case, and in the missingness case about how you can use the insight from the remote audit to actually, go back and try to fix things early. The great thing about these images, these pictures, they're available right now. I can get the imagery for Boston today. I can get the imagery for New York today. I don't have to wait. I don't have to spend, $5 million to get it. I can do it now. So if I do flag these issues early, there's always going to be a way to make your analysis better by incorporating this information, whether that involves re-randomization, which is basically just redrawing the treatment assignment, or whether that's documenting deviations from randomization, or so forth and so on. So this is what you can do if this audit turns out to be negative. If it turns out to be, we have a problem here. So this is some actionables based on that. You might be curious, how does this work in practice? We have two mini case studies here for you before we go on to the next part of the analysis. But these two mini case studies, one of them is about this experiment in Uganda. There are no known issues that I know of with this experiment. We're going to run, in the paper, we run 3 audits, one for missingness, one for randomization, and then one for selection bias. Here on the right are the experimental units, and we use the imagery to predict treatment assignment and among other things. And we find that in this case, the observed change in log likelihood is right here. So the observed value is, a little bit below the mode. And I mentioned earlier that the test that we're using has a one-sided test. Here, ask yourself the following question. We have a negative 1.5, log likelihood difference, and the modal value is about -1. So what does that mean? What that means is that on average, the treatment assignment was actually a little bit less predictable than we expected based on the randomization process alone. So ask yourself, is that good or is that bad? That's actually good. That means things are more unpredictable from the imagery than using than we would expect. So here we would actually pass the test because the observed value of that test statistic is to the left. It's not way to the right. It's to the left. And that's indicative of our test passing. We run another case using that study, that Islam 2019 study that I mentioned earlier, where actually things seem not to be so good. And here we find that when we perform the remote audit using nightlight data and NDVI data, we find that our p-value is actually significant. In other words, we're picking up on something's different about these places that were treated and these places that were not treated. And I should mention here in this youth opportunities study in Uganda, we were using image embeddings from an Earth Observation Foundation model. You can think of the clay model or the new model from Google. I think it's Delphi embeddings. So you can think about using those. We use those embeddings in this case because we have a lot of observations. However, in this case, we only have, I believe, 23 schools. So we have to be lightweight. We can't use a big set of features. We have to use a smaller set of features. So that's why we use NDVI, which is a measure of greenness, and we also use night lights. So our modeling strategy by the structure of the experiment has to be a bit different here, but we're getting some signal that the places that are getting the treatment and those that are not getting the treatment are different, which corroborates those independent concerns from that replication that we discussed earlier. Any questions, any comments?
Yeah, I've got a question.
Sure.
So in this case, the Bangladesh case, you use 2 variables, NDBI and something from night lights. Is that correct?
That's correct.
Predictors for your outcome.
Correct. So those 2 variables are predictors for, I'm just pulling up the deck. Those 2 variables, the image is basically compressed into 2 numbers. In general, if we had more data, I wouldn't want to do that, but in a sense, we're forced to do that by the extremely small sample size here. But you're right. We're taking the image and we're basically collapsing it to just 2 numbers due to the fact that we have such a small sample size.
Right. And from the from the different groups, you found that there's a different distribution of outcomes for those 2 predictors, correct?
Correct. So to walk through the pipeline using this example, we have those 2 predictors. Those 2 predictors are basically a compression or a summary of n. We could use a more complicated summary function, but here our sample size is so small, we use those 2. We use those 2 variables to predict treatment assignment using a random an XGBoost model, like a tree-based model. We use those 2 numbers to predict treatment status. And then so if you think about it, we have 2 columns here Then we have the treatment status column here. These two columns, they're fixed during this process. What is going to change is our random, like the column that contains information about the zeros and ones, indicating whether this village was treated or this village was not treated. So these zeros and ones, we first compute our log likelihood change using these imagery summaries to predict the true treatment assignment. And then we compare that against the treatment assignment if we were to redraw the treatment assignment according to the registered mechanism. So the registered mechanism is basically what they said they did. And we find that if we compare what they said they did against what was observed to occur, we find a significant difference between the two. So what we would conclude from this is we would reject the null hypothesis that the imagery and the treatment are independent from each other under the stated design.
How will you decide on the assignments for each of your different tests?
Great questions. Yes,
sorry.
there was the assignment as it actually. So this is an important point that I should clarify. There are really two modes of doing the audit. There's the ex post, and then there's the ex ante. So there's basically, if I'm actually in the process of running an experiment, the process would basically be as follows. I would generate a randomization, and then I would perform the audit on that randomization to flag potential issues that occurred just by chance alone. Like just by chance alone, maybe all the men and the women, or the freshmen and sophomores got the treatment, but then the juniors and seniors were in the control intervention, or the master's students versus the PhD students. So just by chance alone, there might be some differences between the two groups that we might want to reduce. That's an ex ante version of doing this audit. In that case, if my audit flagged a potential issue, I would want to do something like re-randomization. If I'm doing this ex post like we're doing now, we have the randomization as it was done or purportedly done, and we're comparing that randomization. We have that observed vector of zeros and ones. What I'm going to do is I'm going to go through their paper and I'm going to read what they said they did. We randomize villages to treatment in a completely randomized fashion. So I'm going to take that registered mechanism and I'm going to generate new zeros and ones that follows the exact same constraints as they stated in their registered mechanism. So that's how I generate those sort of synthetic experiments. Those zeros and ones don't correspond to any real treatment or any real control. They're completely synthetic. And the idea is if I'm able to predict the real treatment better than those synthetic treatments, then there was something funky with the real treatment. However, if I'm not able to predict the two any different, that's an indication that the real treatment as it was registered is in a sense corroborated. Does that clarify?
Right. So they gave you the variables.
So here the A they gave us. The A is from the replication package. The M's are our independent data stream that we're bringing to bear on the A's. So you can imagine the worst case scenario. Now I'm doing an RCT. There are different levels to this. So the first level to this is just bad randomization. Maybe just by chance alone, treatment areas and control areas happen to be different. We would pick up on that, but in the worst case scenario, let's say we have a bad actor. In that bad actor, they claim to randomize, but really they're going to their hometown and they're bringing the cash transfers to their hometown. And then to other villages, they're not bringing the cash transfer. Other covariates in the absolute worst case might be affected by potential bias or potential manipulation, but the imagery are coming from me. So the imagery are like an independent data source. I'm coming in with the imagery in my suitcase and I'm using that independent data source to try to check how much randomness there seems to be within the treatment or not. So this is how I see it. It's an independent data source. The M are coming from me. The A are coming from them in the ex post approach. And we're basically seeing how much signal there is in my suitcase, using my suitcase of pictures, how much imagery, how much signal there is contained in that about the purportedly random treatment assignment in the randomization audit. Other questions, comments? All right. So this is the audits. And these are our results, and here are some to-dos about what to do if you get various issues flagged. So that's module 1, design-based inference. How can you use Earth observation data? If in a certain sense, I see the remote audit, it's a powerful tool because it brings independent information to bear to corroborate the design of in particular RCTs, but you can imagine doing something similar for other sorts of research designs too. But now we're going to ask ourselves to more closely dive into this question that Kaz was asking about scales. There's a certain, in sociology, in urban design, in economics, this scale question comes up a lot. What's happening locally is affected by what's happening from a broader perspective and vice versa. And so if I'm growing up in a household that has a certain socioeconomic status, that experience is going to be very different if my household is in a, let's say, richer neighborhood or a poorer neighborhood or a more urban neighborhood or a more rural neighborhood. So there's information about my local context. There's also more information about what's happening broadly. So, my urban design might have different effects on households and communities, and the two might interact in complicated ways. So what we're going to talk about, for really just a few minutes, we don't have a ton of time, and I want to get to the debate as well. But one question that we could ask ourselves is how we combine the best of both worlds, how we combine local information from this household with more global information about this broader neighborhood. And one of the cool things about Earth observation data is that we can zoom in and zoom out at will. We can zoom in, we can zoom out, and that zoom in, zoom out dynamic is something that we can capture. And we can capture that through what we call multi-scale concatenation, which is, when I describe it to you, I hope it feels simple, because we want it to be we want it to be a broadly applicable approach for combining information from these two approaches. Getting to details here, there's some notation here, but I think I can explain it better using just these graphs. Any sort of analysis using Earth observation data, in any sort of analysis using that data, I can do the following thing. Traditionally, I use just one image, and I use that one image to predict the level of poverty. So another one of Kaz's colleagues has been writing some research papers about using imagery to predict poverty across Africa. I could use one image to do that prediction, but I don't need to just use one image. I could use two images too. I could use an image of the household, but I could combine it with imagery from the broader neighborhood as well. So what we call multi-scale concatenation is just a simple way of saying, why don't we just take the image from the household and combine it together with information from the neighborhood to generate a more holistic and improved understanding of what's happening within this household. In other words, we're saying what's happening in this household with respect to poverty, with respect to, you could also do this in a political context, like, will this person decide to vote or not? Whether they decide to vote or not might be, in a sense, correlated with information from what their specific house looks like, or what their, apartment building looks like. But it might also be conditioned by what the broader context looks like. They seem to have a dense road network near them, or do they seem to be isolated? That could affect their decision to vote, or their decision to, become involved in local politics, or whatever the case may be. So this is a running picture of scale in Earth observation. And our approach here is just to combine basically the representation of the smaller scale with the representation from the larger scale. So if we go back to our approach from earlier, if we go back to our setting here where we just used information from NDVI and nightlights, what we would basically do is we would take the nightlight information from this household and combine it with that from this household. But we could also do more. You could use the word complex or sophisticated things using those Earth observation foundation models, or in the extreme case, you could actually just build your own vision model using combined imagery fields or inputs from both. So this is how we could incorporate information from scale. So this is just some notation. It looks complex, but really we can break it down. We're going to preserve local and contextual information by concatenating representations across different patch sizes. So S is the patch size. We're taking the image that's centered at unit I, and we're feeding that into some representation function. That's what this phi is. And we're getting a representation, and then we're just concatenating across the different scales. And what we find, I'll just tell you what we find, and then we'll talk a little bit more about it, and then we'll stop and have debate. But what we find is that if we just use information from one scale, our signal is reduced compared to if we used information from multiple scales. In other words, there's actually a way to quantify how much benefit we get from having like a telescoping zoom of multiple scales, combine the information together within, in this context, the causal inference pipeline. If you're not familiar with causal inference, that's okay, because we'll walk through it. But those are some of the findings that we have. And we attempt to derive these scaling laws about how performance varies as we vary the scale. So This is just a bit of notation for you who are more math heavy. If you're not math heavy, then just go back to these pictures. We have, the zoom in or we have the zoom out. And there's a way to combine information from both the zoom in and the zoom out to either perform causal inference or to do a more predictive oriented task too. So in the paper, we do some simulations. I'm not going to dwell on them for now. The main thing to note is that the black bar is sometimes above the other bars. The black bar is the result we get when we combine information from the local scale and the more global scale in a predictive task. So the paper whose link is up here goes through, the simulation in more detail, but really it's not, the details for our purpose aren't that essential. I think this was a clever simulation design who's on this paper has some clever ideas for how to basically simulate multi-scale dynamics. So if you are interested in diving into more details, I would check out the simulation design here because I think it is pretty clever and Warren did a great job with that. So this is just a placeholder slide. For those of you who are interested in causal inference, this might pique your interest. One of the problems of doing causal inference is that we don't really observe the ground truth. If I'm at OpenAI, I can actually just use my model to predict the next word in various scenarios, and I can get an estimate for performance based on whether my prediction of the next word in my language model was right or was it wrong. Or if I'm trying to predict poverty, I can go back to the ground truth data and I can see, was my prediction right or was it wrong? But with causal inference, we never really know the true treatment effect. We only can observe things that are correlated with it. And there's this emerging literature on evaluation metrics for causal inference, in particular for conditional average treatment effects. So basically, this slide is just me trying to tell you that there is this world out there that provides a way to quantify how much people in an experiment differ from each other, or how much people in my observational study differ from each other in their response to the treatment. Sometimes, like there's me and there's Kaz. Kaz is living in Sweden. I'm right now in Boston, but I also might be in Austin. Will we respond in the same way to the intervention to improve incomes, or will we respond in different ways? That question will be conditioned on a lot of different factors. And this slide just conveys to you that there is a principled way of performing that, of quantifying in my study, given my data, how much heterogeneity am I able to detect from the analysis? So in the sake of time, because we're low on time, I'm not going to dive too much into it, but the basic idea is I'm going to sort all of the observations in the experiment by their predicted treatment effect. And then I'm going to ask myself, how much boost would I get in terms of my outcome if I just treat the top performer? Or how much boost would I get? How much uplift would I get if I just treat the top performer and then the second top performer in terms of treatment effect? So I'm going to sort everybody in this fashion, and then I'm going to average over all the different rules for basically performing that cutoff calculation. And that's going to give me a single number called the rate. The rate is called the rank average treatment effect. And it's just a summary for how much benefit I get from treating the maximum effector, the maximum responder versus the average responder, while averaging over all these different rules for basically defining a maximum responder. So it's positive values indicate I have a strong signal about heterogeneity. If the value is closer to 0, then it's the reverse. I have no evidence of heterogeneity. And so I combine information about uncertainty together with information from the rate in this rate ratio, which is an indication of how much heterogeneity signal do I have while also accounting for uncertainty. Think of it like a t-statistic for heterogeneity. So if you're writing a master's thesis and if you need some way to quantify uncertainty about how different people are responding differently, I would just flag this for you as a potential metric to look into, since it's able to yield a useful summary, even though the counterfactuals, even though the different treatment effects aren't observed directly, if that makes sense. So that's just a bit of information for you about the rate. Like I said, I don't want you to be intimidated by the math. It's really just a way of communicating an idea. And it's just a flag for you in your master's thesis or PhD thesis, or if you do work for, World Bank or various organizations, you could potentially use this to quantify this heterogeneity process, which is useful scientifically for understanding, Cas is different than Connor, but it's also relevant for understanding policy targeting. Maybe I really care about reducing poverty in Uganda. The various, units in Uganda, maybe these people are really going to respond well, but these people are really not going to respond well. I want to understand that so that I don't end up hurting a lot of people by accidentally, maybe the cash transfer makes certain people worse. And I thought I was making them better. I really want to understand that. And this process of calculating the rate ratio is one way to summarize how much signal in heterogeneity you have, one way or the other. Any questions? I should pause and I should wrap up, in a minute or two too. But any questions before we go into debate? And like I said, if you do want to cross-reference these slides, they are available on the website. So just click on that and you should be able to download it. These are the results from the Youth Opportunities experiment that we mentioned a minute ago. We find that in this study, there is, well, I should ask you this, just, in your own mind's eye, so I'll explain it and then I'll ask the question. We have image dimension 1, then we have image dimension 2. Image dimension 1, that's what this is. That's this. And then image dimension 2 is the dimension of that. So what we're doing is we're taking basically a zoomed in image and then a zoomed out image. And then we're varying the degree of zoom in, the zoom in, or the zoom out. So you can ask yourself, what's sort of along the diagonal? Well, along the diagonal, that is basically what happens when we concatenate two identical images. Image 1 and image 2 would have the same scale. So just ask yourself the question, is there evidence of heterogeneity here? Or is there no evidence? Here, on the color, we get rate ratios. Basically, lighter colors indicate a higher rate ratio, and lower, weaker colors indicate a lower rate ratio. And remember, the cutoff for significance is 1.96. So what we find here is that if we just look along the diagonal, if we just used one scale, we find that we would actually get a reduced heterogeneity signal than if we look along this part here, where there is this green star. That's the point where the heterogeneity signal is maximized. That's where the rate ratio is the highest, indicating that in this setting, basically combining the smallest scale of what's happening at the specific household with the biggest scale possible yields the highest signal about how much heterogeneity there is in this particular study, which I think is interesting and indicates that there, in this case, may be multi-scale dynamics operating. However, we had a few different experiments in this paper, and not all of the experiments yielded the same degree of signal, which I'm asking myself, why do some outcomes or why do some interventions yield more versus less heterogeneity? I think that's interesting work for future study. I don't have a good answer for you on that one, but we've thought about it and just haven't really done that follow-up work. But, it could be something worth looking into for sure. We also do a scaling analysis, and this is really one of my last slides. We do this scaling analysis where we basically look at what happens when we take image dimension 1, and then we take the median rate ratio, and then we concatenate, one image, then we concatenate another image, and we concatenate up to 6 different images. So we analyze what happens when we concatenate across up to 6 different images. And we find that the rate ratio actually does continue to increase as we keep concatenating, but there does seem to be a degree of flattening out. The biggest boost really seems to be going from scale 1 to scale 2. After scale 2, it's relatively more flat than it was earlier on, but this does indicate that local information continues to aggregate as we incorporate data from multiple scales. So I think there's interesting work there too on how many scales do we choose. I think in terms of actionables, I would advise at least trying out 2 scales, since that's really where we see the biggest gain in terms of benefit. The intuition is combine features from the local image and then the more global image. That seems to get a lot of the gains from the heterogeneity process. So just putting it all together, what have we done and where are we going? We've talked about a unified Earth observation workflow for RCTs, but also for observational studies. We've covered pre-analysis design checks. We've covered risk scans, looking for risks, looking for potential issues that can then be addressed. We've talked about what to do after we've actually run our experiment and we are looking at the results. And we want to essentially quantify how much heterogeneity there is within the experiment. We've also talked a bit about how do you make this robust? How do you make this pre-registerable? How do you improve the quality of the science that we're trying to do here? I mean, as you know, science is incredibly hard and there's so many potential issues. And this is a unified workflow for how to work towards building up a kind of planetary causal inference paradigm. Oh, There are certainly limitations. For example, as we talked about with CAS just a minute ago, remote audits won't detect everything. A clean result won't be proof of perfection. Also, we found that multi-scale gains depend on the sensor and they depend on the task. And I think there's work to be done on quantifying and clarifying when we see more benefits and when we see fewer benefits. And finally, we've also talked a bit about how this rate is a useful measure that you could potentially use in your thesis or in your policy work to quantify how much different people within your study are varying differently, or maybe not. Maybe they're acting in a more unified way. So interpret this with domain knowledge would be another word of caution. So just wrapping up, key takeaways: think about the design carefully before you move on to the analysis. Think about how information propagates across scales, not just locally, but also at the intersection of the local and the global. Consider deploying insights from these scaling law analyses. Consider using at least 2 scales in your analysis, or at least comparing across 1 versus 2. And then also make things as reproducible as possible. So those are my kind of concluding takeaways that you could consider going forward. I hope you found this useful. Definitely open to questions, open to comments, to debate.
Yeah, thanks, Connor. That was really great. I guess, yeah, should we maybe have like a little discussion about the findings? Maybe we could also, we have some first year masters, second year masters. Maybe we could also talk about like ideas about like thesis, if people are interested in more like causal approaches. So, running kind of experiments. So yeah, maybe we can open up the floor a bit, or any clarification too. I think most of the students don't do causal inference, so a lot of it might be some new territory.
No worries. Questions, comments, or are you thinking about your own thesis? How could your own thesis deploy a similar approach, or what limitations would there be in deploying such approaches to your work? Or if you just want to tell me, I'm just curious about what people are up to. So feel free just to share some of what you're up to as well.
Any questions in the room? I guess I can also ask a question.
Sounds good.
So for the results of the Youth Opportunity Program and the scales, how big are these scales?
Good question. So this is number of pixels on the X and the Y axis. So this is using a Landsat mosaic, which had been pan sharpened to 14.5 meter pixels. 200 refers to the number of pixels, and then each pixel is 14.5 meters in its width. And then, so that's the scale along the image dimension. The color here denotes the rate ratio, which is like the t-statistic that detects the presence or absence of heterogeneity. In other words, if the t-statistic is above 1.96, there is a statistically discernible heterogeneity signal. Here, there are some complications about what stats people would call multiple testing, but we aren't referring to those at the moment. I think there are ways of addressing it, but that's the scale of image 1 and image 2. So 256, what is that? 256 times 14.5. It's around roughly 4 kilometers in width of these images at the maximum. And at the minimum, it's around 200 meters, should be around 200 meters. That would be the smallest scale. So we're going from basically 200 to 4,000. So a 1 order of magnitude change in the width of the image. But the area covered would then be, I guess, 2 orders of magnitude, since the area would go according to the square of the side length.
Do you think this the rate ratio increasing is just a function of the scale, like the ratio of the scales?
That's a good question. In other words, how could we model the rate ratio? I would say it's context dependent. It's task dependent. From the paper, we find that in another experiment in Peru, we find that there's a more diagonal pattern. So there's a brighter color along the diagonal, indicating that a single scale is sufficient for characterizing the heterogeneity process. So you can think about this sort of exercise is almost more like a sensitivity analysis. Let's say for the GeoRDD paper that you're working on, there are different patch sizes that you could use, and each of those patch sizes is going to give a different result. We don't necessarily know beforehand. It's an open question. There's not like an E equals MC squared that should determine for a study of this kind, use a patch size of 200. And there's not even good qualitative work in the literature, to my knowledge, that really covers that. So this is one way of doing sensitivity to basically help us make choices about what scale seems to matter. So in other words, maybe a reviewer gets your paper or your thesis, and they say, oh, you use imagery only of, 100 pixels in dimension. That's not capturing enough information. This is, you could think of it like a simple protocol for getting a quantitative sense for whether my choice of image scale is a good choice or whether it might be a bad choice. And I think the evidence here suggests that it's not necessarily enough to search just across one scale. It does seem to make a difference, one versus two scales. And if you are interested in machine learning or reinforcement learning, I think there are definitely open questions for how we might optimize across scales in a more sophisticated way using, for example, reinforcement learning. Some of your friends maybe your friends work at OpenAI or some of these other organizations, and they're doing a lot of reinforcement learning, which is a way of basically making decisions in a sequential way to get more and more refined answers as we go. And that same approach could be applied here. So maybe it's like three very specific scales combined that give us the best heterogeneity signal. Finding that diamond in the rough might be complicated, and doing grid search might be infeasible as we get more and more choices. But something like reinforcement learning is a way of attempting to reduce the burden of something like grid search, which grid search just means try every single possibility. So here we kept the image encoder fixed, but you can imagine interacting image scale with choice of image model, and things can get very complicated very quickly. So that's really where these reinforcement learning tools might be more relevant.
And I guess in terms of, it looked like the observations were pretty close and clustered together. How much overlap do you think 4 kilometers has on the observations? Like, do you think there's a lot of like spillover or things that are being seen in the image?
Yeah, it's a good question. So here are the clusters. I don't have so in the paper, I wish we had the figures here. In the paper, we look at the fraction overlap as we vary the image scale. So this is all of Uganda depicted. In the extreme case, you could take the image scale to be just the globe, the radius of the Earth, and then every single unit has basically the same image associated with it. So I think there is definitely an interaction between the spatial distribution of units, their overlap, and the heterogeneity signal. We do quantify in the paper what the fraction of overlap is as we vary the scales. It would be interesting potentially, instead of the x-axis here being image scale, another way of doing this would be the x-axis could be the fraction overlap across the different units. And then we could sort of see how the fraction overlap changes here. Early on, like when the image scale is small, the percent overlap is something like 10%. As the images get bigger, I think it plateaus. I want to say at around 50%. I have to go back to the paper to confirm that. In the extreme case, it could potentially get far higher, but I think for most analyses, the image scale is a bit smaller from what I've seen, but at the same time, it would be worth looking into. And I think it's an interesting sort of research question of how overlap interacts with information capacity as well. And you're also right in that, there will be overlap from one image to another. You might think to some extent, it's a problem, especially when it comes to uncertainty estimation. If we have a lot of image overlap, we have a lot of redundant information, and our uncertainty estimates might be inflated. But you can think of it almost like in RCT. If we did an RCT of this class, maybe 50% of people, they're all first year students, and then maybe the other 50% is second year students. All those students have the same feature, just like all the people here might have a similar, if not the same image. Because these are all pre-treatment, we can still perform inference on it. But if the image overlap does increase, we have less information, you get less independent information. It's sort of like if everyone in the class was a first year student, we wouldn't necessarily know how second year students, how they would behave, or maybe we only have one second year student. So that's how I would think about it. I would think about it in terms of, yes, it's contextual information changing. Yes, it's information about overlap changing, but it's also going to affect the uncertainty estimation process and how that will vary our standard errors, essentially.
I guess I was thinking, it's like a half-baked idea, but it's almost like if you have information that like these are siblings and they share the same household, because some of them you have kind of overlapping stuff that it's priving some information to the model about these overlapping spaces, maybe.
Yes. Yeah, I mean, it could very well be that if every household in our study if we have a lot of households in our study and they're all overlapping, the pattern of overlap could be relevant too. So one of the future research directions that we're interested in is how to use imagery for network analysis. If you have the imagery, like if we go back up to here, clearly this house and this house are right next to each other. And maybe there's a pathway that goes from one to the other. So maybe there's a stronger latent network connecting this person, this person. And if we go to this broader perspective, maybe we can infer sort of deeper patterns of relationship. This could be more prominent, especially in contexts where there aren't any roads and where development happens on a more, where foot travel is the predominant form of travel. Then we might see a stronger kind of correlation with structures of network. But that's another thing I would say. There might be signal about how people are interacting, and this might motivate an analysis of that network effect, of that network component. I don't know of much on that. I know of some work on road networks. I think we've discussed that a bit, but it's definitely a greenfield area for those who are looking for thesis topics or looking for side projects. You could definitely explore the network implications of this. Other questions, comments, thoughts?
Yeah, actually. Also, thank you for this talk. It's actually very interesting and we're also a little bit overwhelmed with information. So we're not paying attention or anything. But I think you mentioned, and sorry if I missed this, if you go back to the Uganda chart, you mentioned that Peruvian case study that where along the diagonal those spots or those patches were brighter. And I think I'm a little bit lost on that because having a combination of small and large seems intuitive, right? You got this macro and micro scale. Why would two patches of a similar size, I guess, be better in that case? Unless I'm misunderstanding completely.
No, that's great. A great question. That's totally on point. So I would think about it as follows. So the question, as I understand it, is why would the diagonal ever be good? It seems like, if you have two images that are the same image, it's just redundant information. So why would that ever be better than these other approaches? My answers to that would be, in some cases, there may be truly an optimal scale. There might just be one way of looking at things, one way of seeing this house that is in some sense optimal. If there is one kind of optimal way of depicting or of kind of zooming into this image or zooming into this household, that optimal sort of representation is only going to be corrupted or is only going to be impaired by adding irrelevant information. So, if you think about, let's say the optimal representation is 1, 2, 3. If we add in a bunch of other numbers 10, 20, 30, 40, if we add in a bunch of other numbers, the signal of the 1, 2, 3 is going to be reduced on a relative basis. So that I think explains why things sometimes do lie on the diagonal line. They lie on the diagonal line when there is truly one optimal scale for performing a given analysis, and other information just degrades the signal to noise ratio. And that would kind of push us to lower rate ratio values. So I think that's what the answer is, although could be other processes happening too. But it's definitely an on-point question, and it is interesting. Why does scale sometimes matter, these multi-scale dynamics, but then in other cases it doesn't matter. One interesting follow-up work would basically be to take a bunch of experiments and a bunch of different outcomes and to do this sort of multi-scale analysis, and then to try to predict using meta-level features of the study. Why did this study for this outcome have a stronger signal, but then why did it have a weaker signal for this other study, for this other outcome? Maybe healthcare outcomes, there is no multi-scale dynamic because it's just me and my health, and that's really affected more by my household. But maybe for other outcomes like human capital formation, it matters a lot whether there are other people around me who I can learn from. What matters whether there's a school nearby. So I would say that you could almost imagine that as a grand synthesis. That grand synthesis, I certainly haven't done it, and I would be super curious to learn more about that. But those would be a few thoughts on this question of why this optimal green is sometimes along the diagonal, but then other times it's off the diagonal.
I guess, is the optimal a higher rate? Because in this example, it was quite a good randomized trial, right? So wouldn't we think that a lower rate is better? Or am I reading that wrong?
Yeah, good question. So a rate ratio here, which is what this color represents, a rate ratio it's like a t-statistic for detecting the presence of heterogeneity. So a higher rate ratio just indicates that that there's more treatment effect heterogeneity. So treatment effect heterogeneity, it's not something the experimenter controls. It's just a feature of people. So Kaz and Connor just are different. And maybe your response is really strong to the RCT and mine is really weak to the RCT. There's nothing necessarily wrong in the experiment. It's just a feature of the experiment. And it's a feature of the units in the experiment more than anything else. So that's how I would see it. It's not really good or bad. It's relevant for policy. If there is a really strong amount of heterogeneity, that means that if I just treat everybody, I might be hurting some people, or I certainly would be helping some more than others. But in other situations, if there's no heterogeneity, that means everybody responds in the same way to the intervention. So, for example, if there's like a drug that just works in the same way for everyone, it doesn't matter your age or your race or anything like that. That's a case when the rate ratio would be really small, towards zero, because everybody's responding in a similar fashion. So that's how I would think about the rate ratio, as a sort of signal about how much heterogeneity there is within the context. It's specific to outcome, and it's specific to what data you're using to learn about the heterogeneity. In other words, well, I'll leave it at that. I probably should run it after maybe one or two more questions, since I have another thing in about 5 minutes. But hopefully that addresses that question, Cass.
Yeah, thanks.
I was wondering if there's any limitation on the use of remote audit, because we were just talking about roads, and then I think earlier on you were saying something like when there's correlation between like the treatment assignments being along like the main road. And I'm just thinking like maybe like some countries have this road network hierarchy where there is main road and like secondary roads, or like pedestrian roads. But then maybe some countries or some cultures just doesn't have that hierarchy. So I'm like, how does that play into effect during the
A good question. So I would say, when is it relevant, when is it not relevant, I think is what you're getting at. So the imagery, let's just look at images again. So, there's a lot of information contained in the imagery. Some of it might be relevant to roads and transportation networks. Then other information is relevant to other things. Like, for example, here we see there's a lot of green to this household, and we can see that this is it's not really urban. It's maybe a peri-urban or suburban environment. There's a lot of information beyond roads, and it could be that more accessible locations are getting treated more because of convenience, but it could be other factors too. For example, it could be that the contractors playing favorites and certain sorts of areas are getting the intervention, but not others. Or it could just be a bad randomization draw, that it just so happened that there was an imbalance between the treatment and the control. I would say that there are certainly limits to the remote audit in terms of what it can and can't pick up on. So, I don't think it's going to be able to pick up on all different factors. Certainly, some things are going to be non-detectable, and also certain things won't matter for maybe the amount of nightlife really matters. The amount of nightlight really matters, but other things don't really matter. Like road proximity doesn't matter. With a strong enough learner, with a strong enough machine learning model, in principle, some of those things would be detectable, or the signal could be picked up on, but it would matter a bit what model we use, and also what data source we use and what resolution we use. So in the paper, we talk about how to, using that max T statistic I mentioned earlier, how to combine information from a lot of these different choices. So my answer to your great question would be, it would matter a bit on the context, on the task, on the kind of RCT. Roads might not be the only factor. Sometimes they might be a factor, but other times they might not be a factor. The satellite imagery contains information from this kind of bundle of latent context that contains information about roads, but also additional information beyond roads, is how I would think about it, if that makes sense.
And I think you kind of really went quickly over it, but I think we're moving from this like very hard coded space of like nighttime lights and DVI to then like this like embedding space. And so I think, what we might think about as what we see as the image, and we're like kind of making these captions, like now these like vision transformers are kind of doing these embeddings for us, right? And so I think Connor is kind of trying to say like, oh, there might be roads, there might be other things. And so, we have these information that's coming out as embeddings from these more fancier models now that we can use kind of out of the box, instead of giving like hard-coded like values that we maybe impute.
Yes, no, definitely. That's a great point, Cass. And I probably should run my last point. My last comment on that would be, I think there really is a renaissance of Earth observation foundation models. So like if you are, let's say you're doing a startup, your investors will often ask, why now? And I think one of the reasons why the remote audit now is, I think, so viable is that there really is this renaissance of relatively straightforward to deploy tools to generate these useful representations of images. So I'm sure Kaz will maybe teach you more about those. Maybe he has, or maybe you can learn more about that in your thesis. But I probably should run. I just really thank you all for your attention and great questions. I'm around if you want to talk follow-ups, happy to give feedback on your thesis. The slides are available. We have a book covering this and other things too coming out. So feel free to click on this and receive notice when the book comes out. We every now and then do have, let's say, jobs, postdocs, research engineer positions. Feel free to click on that too if you're ever interested in working with us a bit more deeply. But I just thank you all again and wish you well in your future endeavors.